Welcome. Today I'm going to talk to you very quickly about the master motion equation. It's this one right here. You've seen it a number of times now in the class. I talked about it a little bit. It's, I believe, if I remember correctly, 2.4. I think that's correct. So that's our equation sheet reference right there, 2.4. It's the master motion equation. Why do I call it the master motion equation? Well, the answer is that most often you have a problem in which the inputs that they give you, the things about the problem that they actually give you, are things that are going to end up in this equation right here. So, for example, you've got right here, delta x is, of course, your displacement. Could you have a delta y in there? Sure, of course. Could you have an h in there for height? Sure, if you decide that the reference point is the ground. There's a lot of different things you could have in there. Mr. Lenz, for example, uses a d in there for distance. They all kind of work, as long as you understand that it's if you're looking at it here, the object starts at a position and then moves to a new position. That's the delta x. And so you could call it any of those things. Of course, you could also move from here to here in a vertical way, like so, and you could still have the displacement. That's fine, either way. So there's lots of different ways to reference that. This right here, of course, is the initial velocity. It's an instantaneous velocity. It's asking how fast is it going right at the beginning. If you're smart, when you do experimentation, you pick a situation in which this is going to be 0, because 0 times the time, which we're going to talk about in just a minute, will give you this term dropping out completely, and it makes your math so much easier. This goes from being basically a quadratic equation to being something you can solve with a simple square root symbol, and that's way easier, so do that. Nobody wants to bust out the quadratic formula. I don't remember it. I have to look it up all the time. There's much easier ways to do it if you can. As I just mentioned, that's the time, and of course, you could also reference it as delta t. The reason I don't here is because typically when you start observing something, you start your clock, and so the initial time is usually 0. And so time, this really just means time at the end. So you could, if you really wanted to, you could make it a delta t right here. You could make it t sub 2 if you wanted. Whatever, I'm just going to leave it as time. And this time here is also the same time. They're both referencing the same number. Notice, however, that this time here is squared, and this one is just by itself. So that's an important point. The last piece of the puzzle here is the acceleration, and this is the sort of the average acceleration. So it's not, if it's a changing acceleration, you're going to have to find the average. But for our class, of course, we only take, we have a constant acceleration. We never deal with accelerations that change. Unless they're very, very strange, and then we find ways to try to make it easier on you. So that's all there is to this formula here. Now I want to give you an example of when you might use it. So you might use it when things fall. Okay, so here's my question for you. How far? Okay, so that's the main part. How far? What does that actually ask whenever you see those two words together? How far asks for a displacement or a distance that something has traveled. So hopefully that makes sense. So you can already see that you're going to start to use this equation. Okay, so how far does a ball fall when thrown? So you're actually throwing it downward at, oops, downward, close enough, at, let's say 10 meters per second after, let's say 4.00 seconds. Now, to answer this, you need to know what the acceleration is. So the key is right there, fall. When things fall, they're accelerated by gravitation. So they have this gravitational acceleration, which you might remember little g as being negative, because it's down, 9.81 meters per second per second. So hopefully that makes sense. So here's the question, how far does it fall? Okay, let's plug it all in real quick. So we got our delta x. That's what we're trying to find, so I don't have to rearrange anything. Awesome. Equals the 10.0 meters per second times 4 seconds plus 1/2. Now, this is an important point here. It's thrown downward at 10 meters per second, and so I have to remember that downward is a negative right there. So I'm going to go ahead and do that, negative 10.0 meters per second. So then I can come back to this. Plus 1/2 times g, which is negative 9.81 meters per second times t squared, so 4.00 squared. Okay, so here I have negative 40 when I simplify, 3 sig figs still, plus 1/2 times 4 squared is 8. 8 times 9.81, I'd love to say I'm going to do it in my head for you guys and amaze and astonish you, but that is not going to happen, so just bear with me here when I do that. I end up with negative 78.48. So when I add 40 to that, I end up with negative 118.48 meters because it's a displacement. And unfortunately, I only have 3 sig figs, it looks like. So actually, I'm going to add these two. That is 3 sig figs. So yeah, it's the 10th place. So that's what I have, the 10th place. So technically, it should be to the 10th place right there. There you go. So that's how you use it. Again, if you do it right, you should be able to get rid of this first term if you do the things right. Like if I just drop something from rest, it's going to get rid of that term, and then I can use this equal to that, which works. Hope that helps. Have a good day.